Thank you for that introduction, and good evening to everybody. Can you hear me okay?
Very well.
Yeah, can hear
Okay,
you.
good. Yes, this evening I would like to talk about the work we've been doing to develop various stationary phases to try to optimize the separation of natural product mixtures. The focus of this presentation is really geared towards preparative SFC. I think Mike did a good job of showing some of the power of analytical SFC. And in this work, we're focusing pretty much on the preparative use of SFC. And the goal is to develop stationary phase chemistries to facilitate the optimized preparative separation of natural product mixtures without degrading the green nature of SFC. So again, the focus to us in looking at these stationary phases is try to make it as green as possible. So what are some of the operational parameters that we're looking at when we're trying to optimize stationary phase performance, stationary phase characteristics? We're looking at separation selectivity factor, alpha, minimizing the amount of co-solvents used. Again, reflecting the green nature of SFC and also making it more cost effective. The organic solvents, both the purchase of them and the disposal of them are not inexpensive. One of the things that we think about when we're looking at natural products is, can this be used for human consumption? So one of the things we think about is looking at separations that are based on ethanol, so that if we have to go to human consumption, that we may have some residual ethanol or whatever, but that's believed to be safe for human consumption. We'd like to avoid mobile phase additives, such as TEA. We'd like to look at separation time. In other words, we'd like to develop the preparative isolation in a reasonable amount of time to maintain a quick cycle time so that you can get some stacked injections and really try to get the materials that you need prepped out. Sample loading is an issue, and how much you're able to put onto a particular column or a stationary phase. And finally, we shouldn't neglect the cost of the media. There are some solutions that can be implemented that are rather costly separation or chromatography media. And we're trying to watch that when we're developing these preparative separations, and we're trying to base it upon a more reasonable cost. Chromatography of natural product extracts. Natural mixtures are extracted using various extraction methods, such as supercritical fluid extraction. You can also have liquid extraction. There are other extraction techniques that are used to isolate certain fractions from a natural product mixture. Extracts contain a wide variety of natural components that require further separation and purification to obtain an active fraction or a pure natural product. Chromatography is one of the main methods used to purify natural compounds from complex mixtures. And I just wanted to cite this review. I found this review about a year ago. It's out of the Chinese Medicine Journal, and it is an excellent review discussing the various extraction techniques and isolation techniques for natural products. And if you're working in the area or tend to work in that area, I would suggest that you take a look at this reference where it gives a comparison of the various extraction techniques. What are some of the strategies for natural products? And I kind of broke it, three main ones that I've kind of broken down here is you have the compound group. In other words, you may be purifying a group of compounds such as gingerols found in ginger root, where there are a number of isomers of gingerol, but you're interested in collecting maybe a whole series of these isomers. So you could do that as one fraction. You're also interested in single compound. Maybe there's a curcumin in turmeric root that's viewed as a potentially active ingredient in turmeric root, and you would like to isolate just that one chemical. And then finally, you may want compound removal. And this has been quite a discussion in the area of hemp, where there are amounts of THC that are come along with hemp, and you're trying to produce a CBD product, but you need to remove the THC. So preparative chromatography can be used to, and we'll show some examples of this, to remove THC from hemp and reduce its percentage so that it becomes a legal product for transport. I'm going to show one of our early experiences of natural product separations, and just to show that stationary phase selectivity, particularly for SFC, play kind of a key role in many separations. This is a group of caffeine and caffeine-related compounds found in coffee, tea, and chocolates, etc. Caffeine, of course, theophylline, theobromine, and paraxanthine. Again, these are all fairly structurally similar, so they present a little bit of a challenge to try to isolate a particular compound from this mixture. And this is just one example. This is a separation done on ethylpyridine, which is a widely used stationary phase for SFC. And we could see we're using methanol as a modifier. And we could see that, yes, we can get a separation of the four components, but they're not baseline separated. But if we change stationary phases, and this is a stationary phase that we developed at ES, we call it GreenSep Basic, which is it's a imidazole-based stationary phase. We could get more than baseline separation using the same amount of methanol modifier at a reasonable separation time. So just showing that one stationary phase in SFC can be quite a bit different from another stationary phase in SFC. And the stationary phase does play a key role in determining these separations. And this is just an example of using the basic column. This is cacao, isolation of caffeine and theobromine. So using the imidazole column. This is a little bit more of a complex separation. This is actually isolation of gingerol from ginger root. And this was done with an extract that was purchased. And we performed SFC chromatography on this. And again, we used the imidazole column. But again, I've just identified the 6 gingerol there. But these other compounds are isomers of gingerol. And you might want to collect the 6 gingerol compound, but then again, you might want to collect the whole class of compounds for some animal studies or other studies. So a more complex example would be the separation of quinines found in the tree bark. And this is a natural anti-malarial compound, these quinines. And we could see that they're very structurally similar. They all have a base aromatic structure and then some alkyl ring, some nitrogen groups. So, and they're all structurally very similar. And in this case, the stationary phase that we found for the optimal separation of this group of compounds was a naphthol, which we're used to working with polar stationary phases for SFC, but we found this electron-rich naphthol stationary phase to be very useful for the separation of these quinine compounds. So again, the stationary phase here plays a different role. The current effort that we've focused on has been cannabinoids. And there's been a lot of interest in various cannabinoids, both from the isolation point of view as well as the removal point of view. And based on this cannabinoids, and these turn out to be fairly complex mixtures, we've developed a series of stationary phases where we've made modifications to many of our base stationary phases, such as the imidazole. And we've actually introduced other groups onto these imidazole and some of the other stationary phases that we have for SFC. And now we're calling these the natural product stationary phases. So these have been optimized for particular natural product separations. I kind of view this as very similar to WD-50. If anybody's ever used that, it was the WD's water dispersant, and 50 was the 50th experiment that the chemists had done to get this product to work. So we go through these various natural, modifications of our stationary phases to try to optimize them for a particular natural product separation. And one of the early versions was MP1. Was one of our first attempts, and this is a kind of a whole series of cannabinoids, and we weren't really interested in isolating any particular one there. We just wanted to show that we could develop a stationary phase that had a significant amount of separation power for various cannabinoid mixtures. We then have been involved in optimizing the THC separation from other cannabinoids. The removal of THC from extracts such as hemp are legally important. Materials extracted from hemp or cannabis must not contain more than 0.3% THC to be transported interstate. So we've been approached by several producers of CBD products to try to develop stationary phases to optimize this removal of THC. There are different types of CBD products that are available. One is called full spectrum extract. And this is basically a isolated extract from hemp or cannabis that contains all the cannabinoids less THC. But you can also have just a pure CBD extract, and that's called CBD isolate. The full spectrum CBD extract is considered to be more desirable because you have these other cannabinoids and they may have other beneficial effects. So it's nice just to be able to remove the THC rather than to focus on the isolation of CBD. And I just wanted to, I don't know if everybody's familiar with the various structures of CBD and THC, but I wanted to show them here, and we could see it's just the change of this oxygen linkage to an OH to go from CBD to THC. And the side chain here is the same length, and all the rest of the molecules the same. So they're fairly structurally similar. But given that this separation by reverse phase C18 chromatography is usually pretty straightforward. THC and CBD are well separated. But in SFC, it's a little bit more of a challenge. Again, these are fairly hydrophobic molecules. They do have some polar characteristics. So the stationary phase does play a key role in separating these two compounds. And I just wanted to show, this was some work that was done for ethylpyridine, another widely used stationary phase for SFC. And it actually does perform a good separation between THC and CBD, but there's a concern of how much separation we can get, how much room we can get between THC and CBD. So there was a push to look at other stationary phase to try to optimize the separation of this pair. Also show this as kind of an interesting example where if you go down to 2%, this is at 10% ethanol, the slide on the left. If we go to the slide on the right, it's 2% ethanol, and we actually see a reversal of elution order. So there's some sort of change in mechanism there, and we have not had an opportunity to explore what that change is, but I found that quite interesting. But a better solution would be one of our new MP stationary phases, and we refer to this as MP9. Again, as we go through these different modifications of our stationary phases, we give them a different number. And in this case, we get a much improved separation of CBD and THC. And this again is at 2% ethanol. I put CBN in part of this mixture because CBN is kind of a sink. CBD and THC oxidize to CBN, so there's always a lot of CBN in these extracts. And it's important that we know where the CBN elutes so that it doesn't interfere with the THC removal. So that's kind of a good parameter to have. And again, we're using ethanol, and we're trying to develop these separations with as low amount of ethanol as possible. Now, we have to be careful that it has some ethanol, so it could be actually isolated, and you have some solvent to actually isolate what you're trying to gather. So 2%, 3%, 4%, 5% is pretty reasonable amount, but we're trying to make this as green as possible. So if you go up to very high percentages of co-solvent, you're really degrading the green nature of SFC. So we're trying to use the stationary phase to try to moderate the amount of co-solvent that we're utilizing for these preparative separations. Another approach is we then modified our stationary phase further, and we ended up with this MP10 natural product stationary phase number 10, and we really get quite a good separation between CBD and THC, even better than on MP9. So there are different approaches and different parameters that, people performing these type of preparative separations would be interested in trying to look at. Another molecule that's become of interest in the cannabinoid area is THCV. And again, THCV and THC are very similar structures. The only thing is we have a five alkyl groups tail on the THC and only 3 on the THCV. So again, for reverse phase chromatography, this is not a particular challenge, but for SFC, just a change in alkyl group presents more of a challenge for the separation. And we actually developed another MP stationary phase called MP12 to optimize the separation of CBD and THCV so that we can actually get baseline separation of CBD, THCV, and THC. So the THC and THCV are well separated in this example. And again, we're at 2% ethanol. We're trying to keep the co-solvent to a lower amount. One of the things, one of the compounds that have become of interest in the cannabinoid area are THCA and CBDA. And these are the precursors to THC and CBD. And the plant actually manufactures THCA and CBDA. And then through light exposure and heat, you can form THC and CBD. But there's a lot of interest from the medicinal chemists for THCA and CBDA. And again, we could see the difference here is the acid group, and heat or UV light decarboxylates this acid group to form THC and CBD. And this is an example done with ethylpyridine. And this is at 20% ethanol. And we could get THCA and CBDA to elute in less than 10 minutes using 20% ethanol. The goal of this was to try to reduce the amount of co-solvents that's used and still maintain a similar separation. So again, we went to our stationary phase toolbox, and we developed another stationary phase, MP3, and we get the same separation as the ethylpyridine. And this is the same base silica. So everything is as comparable as possible, except the modification that we made to the stationary phase for MP3. We're able to get the separation of CBDA and CBD THCA and CBDA in less than 10 minutes. And the 2 chromatograms look very similar. The main difference is we're only using 10% ethanol in this example. So again, using the stationary phase to try to maintain the green nature of SFC. And this is really important for preparative separations where you're really using a lot of solvents and potentially using a lot of co-solvent. So in conclusion, we're performing loading studies on the various stationary phases. So there are a number of investigators that are looking to see what size columns they need, how much material they need to actually do the preparative separations that they require. We continue to look at stationary phase chemistry for optimized SFC separation of natural products. So we're always looking for new challenges there. And if anybody has any natural products that they're interested in isolating, we'd be interested in discussing that and maybe looking at modifying our stationary phase chemistries to develop an optimized separation. Again, we continue to look for collaborators and develop commercially viable natural product separations using SFC made greener through the use of stationary phase chemistries. And with that, I'm going to leave it back to the moderator if there's any questions.
Great. Thank you, Matt.
You're welcome.
Any questions? If you have any question, feel free to unmute yourself. So I have a question, Matt. So let's say when you when you have a project, let's say if someone want to separate a particular natural product, do you just based on the structure you design new stationary phase, or you just take your inventory, maybe screen for the stationary phase to see which one give you the best separation?
Yeah, it's a good question. It's actually a combination of both. So we do, I do look at the actual structure of what you're trying to isolate. And so I try to direct it towards one of our main stationary phases that we have in our repertoire. And then we look at modifications that we can make to that stationary phase to try to really optimize that separation. Again, trying to limit co-solvent and trying to really optimize the separation between various components.
Okay, great. Thank you. Now, another kind of related question. So, like for HPLC column, we have this USP classification. So the idea is, let's say, if you have, let's say, similar classification will give you similar selectivity. We know it's not always the case, but like USP, they only, let's say, for C18, they list the L1. Now for SFC column, seems like, you have so many, like a minor difference. So like, is there any classification when people, let's say if I use one column, but now it's no longer available, how do I know which column I should try to see if it can give me similar selectivity?
That is another good question. Again, there's no database right now for similar to what USP has developed for SFC columns. And even the USP L1, like you said, they could be hundreds of C18 phases under L1 and they can all behave differently given for a particular separation.
Yeah.
So again, we don't discontinue any of our stationary phases. So, they're always available for a particular separation.
Okay. Thank you.
I have a few questions. So Matt, this is Mike. I just was curious about the THCA and the CBDA. Do these have any? Are they have any bearing on any effects? I guess any side effects? Is it something that they're easier to handle? Are they prodrugs? Do they turn into the product, or are they not really metabolizable?
That's a good question, and that's really beyond my knowledge of them. I know we've been approached feeling that these are the real precursors that you need to go after to have medicinal characteristics. And one of the things to keep in mind is something like THCV is also available as the acid form. So any of those, a lot of those other cannabinoids, now some of those are oxidation products, so they don't exist in the acid form. but a lot of the cannabinoids that are structurally similar to CBD or THC exist firstly in the acid form in the plant. And so a lot of the medicinal people that are interested in medicinal characteristics want to really go after that acid form and really study from there. So I don't know if that answered your question. That's kind of what
Yeah.
my understanding is.
The other question I have is with the 0.3% tolerance that you have to show it's below 0.3%. Is that require that you run a standard that is a controlled substance? Like you're running THC at as a standard to be able to tell that it's 0.3% by weight or below?
Yeah, the standards that in states where cannabis is not legal, now we're talking about cannabis, so that would be THC. The standards that you're restricted to are 1 milligram per milliliter. So you could buy those standards. I could buy them in New Jersey without any issue. You could get those through Aldrich and ResTech and other suppliers. So what an analyst would do is they would dilute the sample to match the standard that they're able to buy.
Got it.
Any questions online?
Yeah, Matt, this Bill.
Hi,
A
Bill.
couple questions. Yeah, great talk. Couple questions on the CBD and various cannabinoids. So, had you tried using any acetonitrile, and what effect does that have on your separation?
We have not. Again, there's concern about use for human consumption. So and also acetonitrile is not the cheapest solvent. So, a lot of people that have approached us that are in the air that work in the cannabinoid area, they're really focused on trying to use ethanol, but no, we have not looked at acetonitrile at all. And that's a good question, Bill. How does it alter the separation on these various stationary phases? So.
Well, yeah, that actually brings up my next question, which was around, looking at now CBDA and THCA, what effect does any modifier additive have? Say like, ammonia, bubbled ammonia in something like ethanol.
Yeah.
But, what does that have in terms of the selectivity you get?
Yeah, that's a good question. And again, we've not been asked to investigate that. We've been generally asked to avoid any type of additives. So we have not really investigated it or been asked to investigate it, but they're, again, very good question, particularly for the acids. I understand where you would be going with that. That would actually make sense.
All right, and then the last question, I'm seeing it a lot more, just looking around is a lot of people are beginning to just use the chiral columns, the polysaccharides, for instance, most notably for everything. And, have you looked at using the polysaccharides for this type of separation?
Yes, we have, and that gets into the cost of media. And that's one of the reasons why I put that on the slide, is the chiral stationary phases. As you well know, we produce those within ES Industries. They're very costly to produce and make in large quantities. And so we're trying to avoid using that type of technology, and we're trying to use more of a chiral approach to try to do these separations and try to really lower the cost of the media or maintain a lower cost for the media. So yeah, we've looked at, I've actually looked at using, the polysaccharides such as our CCA and CCO and so on. And they do a lot of these separations very well, but then we keep coming back to the cost of the media for what these end users really need to scale up to. That really becomes cost prohibitive for them. In addition, they really would have to, given the expense of the media, they really have to protect their columns. These extracts, depending on what they're using as an extraction tool, may not be the cleanest samples, to purify. So that's kind of what, we've kind of factored that into our thought process.
Okay, thank you.
Matt, I have another question. So I noticed that in one of like in two of your slides, the THC and the CBD, actually the retention order changes. So is this common for SFC separation? Like depends on your stationary phase, the elution order could change.
It depends on the stationary phase. That's a very good point. Yeah. Depending on the type of stationary phase you utilize, you can get these peak reversals and so on. So
Okay.
that's not uncommon. The one example I showed was the 4-ethylpurine, and that's actually a little bit more unique because we actually saw a change in elution order as we changed co-solvent percentage. And again, that indicates to me that there's a different retention mechanism as we change co-solvent. And that's as if somebody would want to investigate that as an academic, that would probably be a very, go into the actual mechanisms of some of these SFC separations. So I thought that was very interesting, but that's beyond what we do in our company.
Thank you. In in general, the column lifetime of the SFC column lifetime, is it comparable to reverse phase or better?
I think in many cases it's better. Depends on, we're dealing with preparative samples here and we're dealing with natural products. So some of these extracts contain a lot of other material.
Mhm.
So that's a lot to put onto a chromatography column. But in many cases, we find that the SFC columns have a better lifetime than many reverse phase columns.
And can they be, let's say, interchanged with, can they be used for normal phase separation and then, come back used for SFC? Or
Yes, and we've actually done that, and we've actually looked at doing some cannabinoid separations. I don't have all the data to present here, but we've been doing some work using these achiral SFC stationary phases in the normal phase for preparative separations of cannabinoids. And the main thing is you have to go through you have to rinse the columns out with ethanol, for example.
Okay.
And if you do that very thoroughly, you're able to remove any of this carbon dioxide. So yeah, you're able to go back and forth between normal and SFC.
That's great. Thank you. Any other questions?
Yes, I have a question about the preparative aspect of this project. Is it kind of, you're working with definitely analytical volumes and concentrations here. Is scaling up I don't know a whole lot about how SFC works as far as a preparative platform, but is maybe could tell me a little bit about what your expectation is on the suitability for that.
Yeah, it's actually SFC, I think in a lot of ways is actually easier to scale than reverse phase chromatography. The going from the analytical size and then scaling it up to preparative size is pretty straightforward. And SFC has one advantage is the back pressure is so much less that we routinely see columns that are 50 millimeter ID, which is a 2-inch internal diameter column packed with 5 micron packing. In reverse phase, you don't do that. The pressure of that column would be pretty prohibitive. But in SFC, we're able to take a 5 micron analytic 4.6 type of column and scale that up in a 5 micron format to 20 millimeter, 30 millimeter, 50 millimeter. So I think SFC is actually more forgiving there than reverse phase chromatography.
What particular type of load would the column take?
Again, the loading is because you're able to utilize the 5 micron packing material in like a 50 millimeter column, you're able to load, gram amounts onto that column, where in a reverse phase that might be difficult to do because again, you have to go back to a 10 micron particle and you don't get as many theoretical plates as you do from a 5 micron particle. So That really is very encouraging about SFC, particularly in the preparative areas, that you're able to utilize the smaller particle diameters. And a few years ago, we actually did some packing of 20 millimeter columns, 20 millimeter ID columns with 3 micron stationary phases. And boy, those columns, you really load quite a bit of material on. So yeah, we're pretty excited. You know, I think any user, you know, Bill Farrell and some of the other people that are logged in here that are big users of preparative SFC could really attest to the loading of SFC. It really is, I think it's much better than reverse phase.